last time we introduced the concept of weak acids and weak bases and what a general acid and general base is. Just a quick little review. Acids, remember, if they're weak, they have a Ka associated with them. Acids react with water to form H3O plus and a conjugate base, all right? We can see that as a conjugate species over here because there's an H plus difference between this and this. This is the acid, this is the conjugate base because this is missing an H plus. This is the base, this is a conjugate acid because it picked up an H plus. All this you should have from the last video. In this reaction with a weak acid, water is acting like a base, right? We also saw base reactions, and a base reacts with water, right? When we have a Kb and it's a weak base, base reacts with water to make a conjugate acid and OH minus, right? The base reacts with water to make a conjugate acid, right? Water forms OH minus as it gives up its H plus. In the top reaction, water is acting like an acid. In the bottom reaction, water is acting like a base. This is a very important property of water, and it really gives us a linchpin, a guidepost for how we approach actually quantifying the behavior of acids and bases, all right? Water is amphiprotic, which another word for that, a synonym, is amphoteric. Amphiprotic and amphoteric, they mean the same thing. They mean a species that can act like an acid or a base, right? So water, we see from our information from last time, sometimes acts like an acid, sometimes acts like a base. It's amphiprotic or amphoteric. And this really leads to some really interesting things about water, because if sometimes it acts like an acid and sometimes it acts like a base, and it just depends what else is with it in solution, what about when there's nothing with it in solution? Pure water doesn't have just H2O in it. Pure water, right, can have a water bumping into another water, right? We know that sometimes water can act like an acid, sometimes water can act like a base. Well, what happens is when a water bumps into a water, an exchange of an H can occur, right? Water's amphoteric, it's amphiprotic, so we can say it self-ionizes. Right? It self-ionizes. And let's say that this water over here is going to be our acid, so it's going to give up our H plus. That means that this water over here is going to be the base, so we're going to add the H plus there. What we get for products, and this happens in pure water, right? A water bumps into a water, and what you're going to get is H3O plus. We're going to get our hydronium ion, and we're also going to get OH minus. So because water is amphiprotic, because it's amphoteric, because it sometimes can act like an acid and a base, it can act as an acid and a base with itself. So in a pure sample of water, this actually occurs. Now, if you notice how I wrote it as an equilibrium. And that's because it's not a strong reaction, it's a weak reaction. And I'm just going to rewrite this, all right? Because this is just showing you what happens. There's an H exchange here. Normally what we do is we write this as 2H2O liquid are coming together to form H3O plus, hydronium, and OH minus, right? This occurs with a K that's labeled Kw. And Kw is an important thing to definitely memorize. And Kw is 1.0 times 10 to the minus 14. So there's an equilibrium that's established inside just pure water where the water is breaking down into H3O plus and OH minus. But let's remember some things from the previous discussions we've had. This K is very, very small. Kw is way less than 1. I mean, it's 10 to the minus 14. If you think about that number, there's like 13 zeros and then a 1, right? When K is small, which side of the reaction is favored? We know that the reactants are favored. So while this happens, because the K is so small, this happens to a very small extent, okay? But it's good to know that there is, floating around in water, a small amount of H3O plus and a small amount of OH minus. So then if this establishes what's in neutral water, then if we make it more acidic or more basic, these values are going to change, right? And that's something I'm going to emphasize as we go through this discussion. Kw is way less than 1. This side is favored. But if we start dumping acid and base in here, we're going to get different values for these species. Just going to rewrite this to give myself more room. Here's how we can use Kw. So in a pure sample of water, let's just do a quick example. In a pure sample of water, how much OH minus and H3O plus exist? What are their concentrations? Well, hold on a second. If you think about how to answer this question, we know that it's a weak process because we're given a K. We have a reaction that we can write down for pure water's behavior. And the two water molecules break into hydronium, all right, and OH minus. I'm trying to answer a concentration question, right? I'm trying to answer a concentration question. And I have at my disposal a K. So guess what we're going to do? Just like our last sections of this course, we're going to make an ice table. Because what we have to do is we have to allow this system to come to equilibrium. We have to take this system and with its K determine how much H3O plus and how much OH minus am I going to make with this process. So let's use the rules from last chapter. What do we do with H2O liquid? Well, H2O liquid, it doesn't have a concentration. It's not an aqueous species or a gas, and so we X it out. So we're using our skills that we learned in the last chapter to actually analyze this new system, okay? Well, given that it's a pure sample of water, so how much H3O plus is there to start? None. How much OH minus is there to start? None. What's Q in this case? Q is equal to 0, so Q is definitely less than Kw. So which way does the reaction go? The reaction goes this way. We're going to get a plus X here based off the stoichiometry and a plus X here based off the stoichiometry. I plus C equals E. I plus C equals E. So if I can figure out an X in neutral water, that X will be the concentration of H3O plus, and that X will be the concentration of OH minus, and I'll answer this question. Again, this is something you know how to do, all right? We know our E information can go into a Kw expression. Kw is 1.0 times 10 to the minus 14. This doesn't show up. It shows up as a 1 in our K expression, so I'm just going to kind of leave it out. Here are my products. It's X times X. It is X squared. So this is one of the easier ice tables we'll solve. All we have to do is take the square root of both sides, and we get that X is 1.0 times 10 to the minus 7th, right? This is incredibly important. In pure water, all right, let's answer the question. What's the concentration of H3O plus? What's the concentration of OH minus? Pure water is said to be neutral because the concentration of H3O plus, which we know is generated from acids, and the concentration of OH minus, they're both X, they're both equal. They're both equal to 1.0 times 10 to the minus 7 molar. They're both equal to 1.0 times 10 to the minus 7 molar. Now that's a mouthful, right? But it gives us a guidepost. Again, if I throw more acid in here, this is going to go up, this is going to go down, and these numbers won't be equal anymore. This is only valid for pure water. Likewise, if I throw some base in there, this is going to go up, this will go down, they won't be equal anymore. But for neutral pure water, this is the concentration. So this is kind of annoying to keep saying. And like I said, it establishes like a guide here. Okay, so how can we use this again and again? Well, instead of having to say 1.0 times 10 to the minus 7, what we do is, with this information in mind, we establish what's known as the pH scale. Because we'll see that we're just going to put numbers to all this that are a lot easier to say, a lot easier to write. So here's how the pH scale works. We know for water, right? If you look at that expression for water, so look at the equilibrium expression for water. In that last example, what we had was Kw, right, was equal to the concentration of H3O plus at equilibrium, which, remember, that was an X, times our concentration of OH minus at equilibrium, and that was our X. So what we did is we just went in and throw in numbers, and in the last example we wrote 1.0 times 10 to the minus 14 here. We wrote an X and an X there, so that became an X squared. But this is really what occurs, okay? So this is a true statement. We can use this over and over again. So what we do is we invoke this mathematical operation that we're going to signify with small p. And whenever we see a small p, and we'll see it in a couple different ways, right? When you do a p of anything, so this stands for anything, and you can do it to any number you want. What p means is it means the negative log of whatever that is. So this can be anything, and we'll see what we mean here in a second. All right, we're going to go for pH, right? pH is eventually going to be the P of the H3O plus concentration, right? But just know this, whenever you see that P, small p, before something, it's saying, hey, the math that we do is a negative log. And it's just going to be a way to actually kind of organize our thoughts. This is good to know, all right? But let's take the negative log of both sides. If I take the negative log of Kw, then I have to take the negative log of this product on this side. Right? On this side, I have negative log of Kw. Well, wait a second. I just said that the negative log of anything I can write as the P of that. So the definition that I established for what that mathematical operation P is, the negative log of Kw must be pKw. All right. Over here, I'm going to use, okay, here's a log. Inside, we have a multiplication. I'm going to use some properties of logs here. I'm going to break this into the negative log of H3O plus the negative log of OH minus. Remember that log rule that we have? Well, if we have an log of two things being multiplied, we can turn it into a sum. So you're saying, okay, well, why is it a difference? Well, if I just take this negative sign, I'm going to turn this into a sum. But remember, the negative sign multiplies everything, so you distribute it to each part. Okay? So now we see that on this side, we maintain our pKw. This is the negative log of H3O plus. This becomes a very important thing for us. We're going to call that pH. All right? Now, where did the negative go? Remember, the negative is part of the P. Same thing over here. This is the negative log of OH minus, right? Using that definition for P, the mathematical operation that I introduced, the negative log of OH minus must be POH. So all I do is I translate using that definition. Negative logs, I can write as P's, and I get this very important idea out, that pKw for any aqueous system, right, even though we're basing it in pure water, this will be true for any aqueous system, pKw is the same as pH plus pOH. Okay? Kw is the same as H3O plus concentration times OH minus concentration. This is also valid. It's just this ends up being a little bit easier to use, and so we establish a framework to use pH and pOH and pKw in their relationships instead of sticking with concentrations entirely. Right? So let's just kind of take a look at this with the results of the last example. All right? With our last example and pure water, right, what we found was that we knew these numbers. Okay? So from our last example, and I'm just going to write this above, remember how we knew Kw? We knew that Kw was 1.0 times 10 to the minus 14. And with pure water, and only with pure water, what did we know? These two were equal to each other, and they were both equal to 1.0 times 10 to the minus 7. And now we see how this equation holds. If I plug this in my calculator and I multiply it by myself, or by itself, all right, you'll get this value here. That justifies this formula. Now what I want you to do, and I want you to practice it, I want you to pull out your calculator, and I want you to put in 1.0 times 10 to the minus 14, and I want you to take the negative log of it. And that will calculate for us pKw. So if you do minus the log of 1.0 times 10 to the minus 14, your calculator spits out 14. Now remember our log rules for significant figure purposes. There's two significant figures here, so when I do this, there'll be two significant decimal places in my answer. So pKw, right, pKw is 14.00. Now do the same for 1.0 times 10 to the minus 7. Take the negative log of it. What you find, paying attention to correct significant figures, is that for that neutral situation, the pH was 7.00. Right? For that neutral situation, if you put 1.0 times 10 to the minus 7 into your calculator and do the negative log again, you'll also get 7.00 for that neutral situation. Right? What you have is a situation where the pOH is 7.00. So we see with that example that we did, pKw, 14, is equal to pH plus pOH, right? That's the same, it's just equivalent. So the reason I'm kind of showing you this is that these expressions are equivalent. We're just looking at them in different ways. And instead of saying like 1.0 times 10 to the minus 7 molar and having to keep track of all that, it's way easier to say 14 is equal to 7 plus 7, realizing what the mathematical operation P indicates. Now, I mentioned it before, this is only for pure water. What happens when we have an acid or a base? These will change. And here's how the pH scale works. There's a pOH scale too, but we like to just kind of stick with the pH scale, all right? For pH equal to 7, what we just shown is that this is what we're going to refer to as a neutral situation. That's where the OH minus and the H plus, the H3O plus, are equal to each other, all right? Yeah, I just made mention of that. Why is this pH instead of H3O plus? Chemists get lazy, right? Inside the actual reactions going on, there's hydronium, H3O plus, right? But what they'll say is H plus aqueous means H3O plus aqueous because the aqueous implies that there's water there. So they'll take an H2O away from hydronium just to be completely lazy and write it as H plus. These two things mean the same. Whenever you hear about an H plus or an H3O plus in solution when you're analyzing things via pH, they mean the same thing, all right? So if our pH is 7.00, we have a neutral situation, all right? What happens when our pH, all right, is less than 7.00? And what we have to remember is that this is a negative log scale, and I'm going to show you an example in a bit here for how this affects things. But if I just take a look at the pH less than 7.00, this is what we're going to refer to as an acidic solution. And that's because the concentration of H3O plus in that solution at equilibrium is greater than the concentration of OH minus. So pHs below 7 are acidic. When we have a pH that's greater than 7, those situations are going to be basic. Now, why are those basic solutions? That's because your H3O plus concentration is less than your OH minus concentration. Knowing this is incredibly important. We'll be able to decide whether something is acidic or basic based off the pH, right? Just to kind of show you an example to work some numbers here, right? A solution at equilibrium contains 1.0 times 10 to the minus 6 molar H3O plus. All right, what is the pH? What is the concentration of OH minus? And we'll know that from the pOH, right? So now that we have the pH scale established, all right, we can start to ask ourselves these sorts of questions. Okay, let's also ask ourselves this. Is the solution acidic or basic? Now, we kind of know that from the start if you're paying attention and you're comfortable with things, right? We know that from the start because if you look here, remember our guidepost is neutral water. And in neutral water, the concentration of H3O plus is 1.0 times 10 to the minus 7. So this right here, this is actually bigger in concentration than 1.0 times 10 to the minus 7. So right away we know it's acidic. But just to emphasize some things with the pH scale, we're going to go ahead and prove this in a couple different ways. All right. So let's go ahead and let's calculate the pH together. All right. Get out your calculators. Oh, I know if I want the pH, I'm going to take my H3O plus concentration. I'm going to take the negative log of it. All right. Remember, we dropped the molarity. All right. We just pretend the logs don't have units. When I plug this into my calculator, I get 6.00. The negative log of 1.0 times 10 to the minus 6 is 6.00. Remember what we just established in terms of the pH scale. This number right here for pH is less than 7. So what do we know? We know it's acidic. And even though we knew that from the top, we're just showing you how the pH scale can be used to decide whether something is acidic or not. Okay? So now, how can we use the pH scale to get at this other information? What's the pOH? What's the concentration of OH minus? Well, do you have this very important relationship that's already established in this video that relates pH and pOH? Well, sure. 14.00, which is pKw, equals pH plus pOH. All right. And I'm just going to erase some stuff at my top here so I have some room. So, if I know that this is a truth, no matter what, okay, and now I have pH, what I can do is I can take this number and I can throw it in there. And so for this particular acidic solution that we're looking at, 14.00 looks like 6.00, right? That number that we got for pH plus pOH. So we can do this math real simply. pOH is 8.00. Now, how do we get the concentration of OH minus from there? We get the concentration of OH minus from there by doing an anti-log. Because where is the concentration of OH minus hidden? It's hidden in the P. And remember, whenever you see a P, you can translate it into the negative log right, of that information that's being passed to it. So for this particular solution, we kind of go in the opposite direction. The negative log of OH minus is equal to 8.00. The log of OH minus then is equal to negative 8.00. How do I get rid of a log? I raise both sides as a power of 10. Now look what happened here, right? And this is a step that's often missed, so I'm going to point it out again. Remember, POH has a negative log. You take the negative to the other side, and then you do the anti-log. So when I do the anti-log here, these two guys are going to cancel, and I'll be able to solve for OH minus. Remember our anti-log significant figure rules. You look for the significant decimal places here. These become the total significant figures here. And what you get out of this is that the OH minus concentration in this solution, right, is 1.0 times 10 to the minus 8. And then we remember that at the end of the problems, we report the units. 1.0 times 10 to the minus 8 molar. So knowing how to go from a pH to a POH to an OH minus concentration is something that we'll do again and again. Just to finish off this video, there's a lot of important stuff here, and you're going to do a lot of practice with these sorts of problems and manipulations. But I just want to point out that there's multiple pathways for information, right? Another way we could have done this another way we could have done this example is if you look at the information that was given at the top, the H3O plus concentration, right, was given as 1.0 times 10 to the minus 6 molar. We also know, and I just wanted to show you how to use a pH scale, we also know that Kw is equal to H3O plus concentration times OH minus concentration. We also are going to be good students and memorize Kw as 1.0 times 10 to the minus 14. So then if I have 1.0 times 10